Hey everyone. So for me, it is very, very early on Wednesday morning. Filming your lecture for Thursday the 16th, because today's the 15th. Because I've been asked to provide lectures online for the first few weeks, but I also have been told that I have to be in person during the class time, even if I'm not giving a class. It means that the only time slot I have available to film this lecture is very, very early on Wednesday morning, where I had some unwell kids on the weekend. It's kind of jammed my hours up a little bit, so I apologize that I might be a little bit tired. My hope was always for Dave and I to give as many of these together as possible. The fact that the kids are asleep upstairs, and I desperately need them to be well rested for school because they can get sent home for appearing tired sometimes. I need them to sleep until 7:30. It's about 4:30 for me, so I'm going to film the first half of the lecture. Dave will be sitting here. He'll pipe in. Dave, you can just raise your hand and wave because we can practically see you. But he'll be on kid duty for the first half because they'll inevitably wake up. And then I'll be around while he films the second half. But I'll get lunches ready for school and pack backpacks and then be on duty to go deal with the small children. So today's lecture is stairs, and more stairs. This one also introduces us to the method that we're going to use for this course every time we talk about at least some of the main features. So what I will try to do, let me get it so it'll click over. So what I'm going to do is I'm going to introduce all the criteria we use when designing these feature elements. So this week it's stairs. We'll look at the strength criteria, and you guys all remember that strength is life safety. Then we'll look at the serviceability criteria, if there is any, and if not, when it should be applied. Within serviceability, we normally lump vibration, but because for stairs it's such a critical thing, I've actually pulled it out and made it its own category. And then we'll also look at stability. So we'll look at the free body diagram of a basic stair. And then what I'm going to then I'll talk about the different types of stairs you can have. And then I will talk about, I'll go through a series of stairs. So I have a bunch of photos of stairs. The first few are going to be case studies because they're ones I've designed. So I'll go through, okay, on this practical stair, this one that was actually built, what did I do for strength? What did I do for serviceability? What did I do for vibration if we chose to look at vibration? And what did the free body diagram of that particular stair look like? And then I'll show you the analysis, kind of what my model looked like, the various stages of drawing development, how we issued this information and communicated it to the builder, because we're into feature elements now. The rules aren't as rigid on how we present information or communicate with our team. There is one stair where it's a very kind of normal process. So one of the stairs was for a large group, following all the normal issues where people are going to question tender, and so that one in some ways is more rigorous because you still have some of those building processes to follow, even though it's not the building itself. And then probably the last third of the slides in this are just literally pictures of stairs from the internet. I went through and found the coolest, neatest stairs I could find. Some of them are actually ones that Dave or I have designed. Some of them are ones in Toronto that people we know have designed. Some of them are just cool stairs that are either famous or ones that we found really cool. And Dave will talk about a lot of those. He'll probably not be able to help himself and pipe in periodically while I'm talking as well. Um, so let's dig in. So the first thing is strength. What strength loads do we use to design stairs? Well, in houses, we follow the normal house load, which is 1.9 kPa. Now, that said, I always think about what kind of owner is making use of this stair and have a conversation with the architect or even the owner about it. If it is very much residential and it might be a feature stair or even just a regular stair in the house, is it just a normal size house with, they might have a party, but it's a house party. Even if it's the fanciest house party, you're going to be hard pressed to reach over 1.9 kPa. If you're talking about a feature stair in a house that's more like a mansion, you're probably going to want to think about 4.8 kPa, because those are the times that they will have a gigantic party, or they'll rent it out for something and there will be video shoots of a party and they will try to make that 4.8 kPa. I know you're thinking, why would you design a stair for a fake video of a stair usage? That was just one I could think of, but I can think of feature stairs in very, very large houses where they would host the sort of party where they could do 4.8 kPa. I have one stair in this where I know for a fact that they wanted the stair to be able to use for photo shoots as well. So I'll show you that one when we get to it. So for everything that's not in a regular style house that will have just kind of regular family or friends style party, we would use 1.9 kPa. Everything else we would use 4.8 kPa. If it is neat, so then you have to ask yourself the question, does it need to be fire rated? Remember, combustibility and fire rating are not the same thing. Fire rating is how long does it have to maintain its strength in the event of a fire. That doesn't necessarily mean it needs to be non-combustible. That said, most fire-rated stairs also need to be non-combustible. Not always, but usually they do. Now, that is digging into the code in the fire zone, which I will admit we are not experts on, but we actually have the luxury of being more exposed to it than you guys do because we work on so many projects. So if an architect is designing a feature stair, I might be working on 3 feature stairs because my scope in it is actually smaller than the architect's scope. They're fitting it in usually to a larger project. So my scope is smaller, but my exposure is greater. So I know some things about fire ratings. That said, fire rating is the architect's scope, and often we'll have consultation with a code consultant on fire rating for those issues as well. So I can give some hint of feedback on that. If your stair is the exit, the main exit, or the only exit, it needs to be fire rated. If there are enough fire rated exits in the building, your feature stair might not need to be fire rated, as long as you meet all of the abilities of people evacuating the building, not needing that feature stair. And that can be really important because some of the fire rating criteria means that you have to be kind of encapsulated or separated from the rest of the building, which you can imagine for a feature stair, which is out in the open space, you don't want to then drywall it in. So that's why you might need other exits, and then that stair might not need to be fire rated. So what are our serviceability criteria? The standard criteria is L divided by 240 for dead and live, and L divided by 360 for live. So what do you do for length? Because there can be all kinds of different kind of formations of stairs. Well, sometimes it takes just a little bit of thought. You might want to look at what the absolute limits are. Would you want to be on a stair that was allowed to move an inch? Probably not. It would feel very unpleasant. So we apply the standard criteria, use some judgment and discretion on what its application is on, and then sometimes we'll apply some absolute limits if we think that's relevant. Vibration. Vibration is really important on things that don't have a lot of finishes or a lot of connectivity to other things. We always worry about vibration. It's just that we often have so much stuff on our building elements that vibration doesn't rise to the top of the design checks. Most of the time in Canada, for most elements within the building, vibration doesn't govern. We give it some thought, and then once we know that it's not a high priority because it's not going to be the governing situation, we stop forgetting about it a little bit. Stairs and pedestrian bridges are very susceptible to vibration criteria. So what does that mean? I always start with a conversation for a feature stair when applicable. Is this something that the owner is going to be annoyed about? Because I have had owners that have said, I don't care if I can feel it move. I want the fanciest, thinnest, most refined stair possible. And if I can feel it when somebody else is on the stair, I don't care. I will sacrifice feeling someone else on the stair for great design elements. If we have a stair that is in a public setting, it doesn't matter. We want to meet the tightest, the most stringent vibration criteria possible. If it's a serviceability, if it's not a feature stair, but a serviceability stair in the back of house where you're going up to monitor the air conditioner on the roof twice a year, maybe we don't care about vibration criteria. So what are the vibration criteria? Well, there are two main criteria and one that we break down. Essentially, what we're saying is, for the first one, if you're going up the stairs on your own, how does it feel while the stair is moving or vibrating? The other one is, if you're standing still on the stair and somebody walks up, how does that feel to the person standing still? And we actually look at two different criteria for that. We say one, okay, well, we'll accept that this is a feature stair and we just don't want it to be bouncy while the other person walks up the stair. If this is more of a public setting, we actually look at the criteria where one person's standing on the stair and another person actually runs or bounds up the stairs. The equations are quite complicated. You can see here that there's a lot going on with very kind of intense equations. I am not making you do these equations. If you've been sitting here for the past few seconds slowly sweating in terror, we're not going through those calculations. I'm going to show you some of the ones I've done, but I've created my own spreadsheet for this analysis. I know Dave has his own spreadsheet for this analysis. I recently worked on a stair where an engineer who let me know how long he's been in the business and reminded me that I'm just a young girl in this industry, also had his own vibration spreadsheet that he had built. So engineers usually kind of go through, dig through it rigorously, and then make use of their design spreadsheet. The key with it is some of the fundamental issues that you start with, and this is where you can get a wide range of interpretations. There are a few criteria that are subject to interpretation. The first thing is what's the load? Well, the load they actually provide for us. So it is a 0.75 kilonewtons or 168 pounds. The code is set up in imperial. It's not even a code. It is it's a vibration guide is more the way I would refer to it. So it's not like a life safety issue where it must be met, but it should be met. We have had ones where we have met this criteria and still we had an owner come back very, very angry saying that their stair is very bouncy and they want to sue everyone in creation. That's one of the downsides about doing feature elements for very, 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 very rich people, is that sometimes they will make that decision. So it's really good to understand your client and explain to them how this goes. So the guide for vibration, it's not vibration isn't a problem. What they look at is a moderate range of people and how they feel. It doesn't mean somebody with an inner ear problem won't find this vibration disturbing, but we consider them on the outside range of what is normal perception of vibration. So you will still get people who thinks these vibration criteria aren't stringent enough. It is about satisfying the majority of people. So that is why vibration is always a funny little dance about communication with clients. So the other things that are up for interpretation. So this is one of my vibration looks. So you can see that I've pulled from that code what I'm looking at here, and then put it right into my spreadsheet so I have reference to it. So the first thing is, what is the frequency of our stair? Now there are very complicated ways to so frequency is just the inverse of period. Period is usually calculated through that design guide, but also it can be done in an analysis software. So I use eTabs as my analysis software, and within that I can pull out the vibration, I can pull out the period of the stair under the load cases I'm looking at. This is where, for that particular stair that I was talking about, where the person in question reminded me that my age and gender might not allow me to make good decisions about stair design, that he had just followed the basic code and I had done an actual analysis of it for frequency. One of the other things is damping. So damping is what stuff is attached to our stairs. Unlike strength, we get to say all the stuff that goes on it actually helps reduce our vibration of our stair. So you're throwing tile floor on it, carpet, a big stiff handrail that's connected all the way along, risers in between your treads. All of that can contribute to the stiffness of the stair, which is going to help impact the vibration performance of the stair. So picking your damping ratio, remember damping was when we did that heel drop and felt how the building shook around us. That is about picking the correct damping frequency. So if somebody is standing on the stair and they step on your step, yeah, you'll feel the vibration, but when they're on the next step, the damping doesn't allow it to impact you quite the same way. So rather than feel the vibration the whole way while that person's running up the stair, you might feel it for only 2 or 3 steps, which people get. They understand that. They're okay feeling that issue. And so you can see here I have my normal criteria of you walking up the stair, the fast criteria of somebody running, and the fast criteria of somebody walking beside you. So I should probably change the way I've called that. I understand what I'm talking about. Also, the weight of the stair. The actual weight of it helps impact damping as well. So there's a few things that really go into it, and small changes can have a big impact on it. So just a basic free body diagram of the stair here. Normally we're looking at the stringer, and I'm going to break down the stair elements in a minute, but this is 2D, so obviously there's another stringer in the background. I'm looking at one stringer here. How you choose to do your reactions on a stair, whether it's pinned roller or pinned, can have a very large impact on the loads. Normally when we were talking about just a normal beam, it doesn't have much of an impact. When we were looking at trusses in past years, and we didn't even really get into that, But for a truss, doing a pinned roller is really important. If you try to do pinned and don't allow any movement at one end, kind of in the length of movement, you can stop the truss's ability to deflect, which actually imposes very high compression and tension forces in your top and bottom chord. Stairs, if you lock these in as a pin instead of a pin roller, you can actually develop very, very, very high reaction forces. So we'll often, where possible, look at doing a pin roller. We will actually analyze it with the load on it and see what the movement is. If the movement can be, a millimeter or two, because we've allowed it to move, often we'll put the reaction up here and the roller down here. And if this is allowed, if this moves just the tiniest little amount, we're good. If this tries to move a meter, well then we have to do a pinned condition, and we will probably develop very high reaction forces. I'm just thinking I should go back and for next year add in, I have a stair very specifically where that was the case. We couldn't allow any movement at the base the way they were detailing it, and it did have to be locked in, and we did develop very, very large forces there. So I'm going to just talk about types of stairs, just kind of how we talk about them, what the stair kind of assembly is, just so that we have some of the verbiage right on what stairs are. So the stair basics. Our tread is this thing we put our feet on. The riser is the height between step to step. Some codes allow you not to have a solid piece in there or some element in there. Some are getting very particular, saying you can't have open risers, which means no risers. And in fact, the Ontario Building Code just is in the process of implementing that. Stringers are the thing that span from floor to floor and support the stairs, or support the risers and treads. Landings are where your stair connects. You might have a mid-height landing as well. Guards. Now, guards we're going to talk about in an entire separate lecture. Sometimes for strength, depending on the type of stair, we will say that the guard is a beam. So if we have a solid element there, we can actually make our stringer and the guard one large thing acting as a beam. Most of the time, we just have an element attached to our stringer. And in that situation, we can't use it for strength, but we do get to use the guard for vibration if it's going to help us. And handrails are separate. Often they can be the same thing as the guard, the handrail and the guard element. Sometimes they're the same, sometimes they're not, but they have their own design criteria as well. And we'll look at that. I think it's next week that we get into guards. So we'll talk about guards and handrails in depth. But I wanted you to see that not always, but they're not always on the stair. Sometimes they're at the opening, but sometimes they're on the stair themselves. So I just wanted to get the verbiage going. And then pickets are the elements kind of in between the guard upstands and the guard top rail. So we can have wood stairs. Here you have very standard construction. And see we've got a mid-height landing. This one's been connected to the building here. So we've got 3 points of support. We've got the upper floor, we've got the landing attached to the wall, and we've got the floor here. Sometimes these are not actually connected to a wall there. So you'll see that often in switchback stairs where there's no wall. Here is a steel stair. Often for a steel stair, our tread will be either just a piece of grating, a piece of steel, but often what we'll do for wear surfaces, especially in public stairs, we'll see it be a pan that gets filled with concrete. That concrete also helps with damping of the stairs. So here is actually some images of treads. So steel treads. We can have concrete in a metal pan. So here there is one piece of steel. This one kind of goes up and turns into our riser as well. You can have concrete in a metal pan without a riser. This one looks like it's a metal pan with so that one they have a prefabricated piece of steel or prefabricated piece of concrete fastened to the steel pan. This one is steel plate or aluminum. Sometimes they have drainage holes in them, sometimes they don't. And these are different styles of grading as our stair. Risers, if you have them, will often match the entirety of it or the substrate. So unless you're doing a cast in place stair, you wouldn't have your riser be concrete. So if you do have a metal pan, you'd also often have your riser, if you have it, be something that matches, or it might be an open kind of expanded grate style element. So the stringers. Stringers, we can have lots of different styles of stringers. The most common is probably 2 channels turned out that allow us to weld the pan to. So you can see that right here. You can see our channel with our flanges turned out like that, and you can see the piece of metal here welded to either of the stringer side. We can do steel HSSs here on the side instead of the channel. We often like the flat side in so that it's a little bit easier to weld to. So this channel could be an HSS. We can do a single stringer, but if we're doing a single stringer, we have our teeter-totter problem happening. So you can see that if somebody was standing here, that stair wants to twist, and this now is a torsion element. So we need something that is a closed section so that it can twist. Wish I had something that demonstrated how closing a section improves torsion. Can you think of a practical example about
those crappy little curtain rods you could buy that were an open section? Do you know the little tiny curtain rods about that big?
I can't think of ones that are an open section.
They were really crappy.
But you've probably experienced it where something isn't, and so open section means that it doesn't have a solid kind of hole within it, whether it's square or rectangular or oval or circular. That kind of closing of the loop gives it some torsional rigidity. We then have to connect it for torsion at the ends though, which is a style of kind of combination of moment and shear. So it can have torsional stiffness, but then we have to connect it for torsion as well. We can drop our channels underneath. This one's neat. This one's one where the tread is actually hung from above, from something above. We can do individual treads cast into concrete, whether it's wood or whether it's concrete or fastened to wood somehow. And here's another one where we have a single stringer where it's at the center of the stair, but we still have our torsion issue that we have to worry about. Landings. We can do concrete on metal pan. So that's this stair here. This is metal deck sitting in a steel frame, and then concrete came and got poured on this at a later date. We could do concrete, this one was concrete on metal deck. You can do concrete on metal pan. This one was large, so we wanted the metal deck. If it's a small enough landing, you can do metal pan similar to the stairs or to the treads. You can do simple wood if your stair is wood. So you saw that one where we had a wood landing a minute ago. You can do steel grating if it's a slightly more industrial style stair. Grading has ratings provided by the manufacturer, so they're proprietary products, and every different grading supplier is going to have a different load table catalog of what that can span. So if you were the architect and you said you wanted metal grading, I would say, what style of metal grading are you looking for? And then once we established that and the brand you were imagining using, I'd go pick out what one worked for the spans we're talking about. You can do normal steel framing and then clad it. You could do extruded aluminum profiles and infill it. Most of the time, we match what the stair treads construction are in some way. So the form was slightly different. So this one was a pan, this one was metal deck, but they're both being filled with concrete once they're completely in. Cast in place concrete. So the key with cast in place concrete is its effective thickness. So the effective thickness is what is doing the work from spanning from one end to the other. And often, if we're keeping it simple, we will make the effective thickness the thing that is consistent and doesn't have any jogs in it. This allows us to have relatively simple reinforcing. As you can imagine, it's just straight pieces of reinforcing. And for something like this, the reinforcing would be nominal, and the cost would be in how beautiful do we make these finishes. You can cast the underside, but this is now just some formwork. Well, not just some formwork. The formwork's going to be expensive, but there's cost in the formwork. It's not often done, but it can be done because the reinforcing work for something like this is extraordinary. Here, this is our effective thickness, but we now have to bend our reinforcing. We have to still be able to develop our lengths. So this isn't as common. It can be done, but it's going to be very expensive still for formwork and for reinforcing. Here we only have expensive formwork on the top. Here we have expensive formwork. We have expensive formwork on the top and easy reinforcing. Here we have expensive formwork top and bottom and easy reinforcing. Here we have expensive formwork top, bottom, and very complicated reinforcing. Just to give you an idea of a simple stair, so this is a relatively simple stair. I guess this one was a normal span. It's connected into a wall here and here. So yeah, it is this stair here. Look at how much reinforcing is in this. So this isn't mine. I found this on the internet. But you can see the amount of reinforcing that goes into one that has a relatively normal underside. So we have a regular effective throat. This was, if we go back a slide, this style of concrete stair. So you can imagine if we then go into the complicated reinforcing, what this would start to look like. You can actually have precast stairs as well. So the advantage of that is you have very, very smooth cast concrete. The disadvantage is that one of the normal advantages of cast in place is that you don't see any fasteners. It's seamless with the rest of the concrete building. Here we now have fasteners. If it's a cast in place building, it's going to look different than the rest of the concrete. I've seen cast in place stairs in steel buildings. It's not as common, simply because you also now, the advantage of precast is that you can bring it in later and install it. But if it's inside the building, how do you actually get it in? Because if a steel stair, you can bring it in pieces, assemble it in place. Because stairs are often the last part of the project. In the short term, they usually build like a rickety wood temporary stair. Just want to see. Okay. So stair types. This, I went to a website that called Dimensions Collections, Stairs and Stairways. So this is a series of images of types of stairs. So, straight run stair. We start at the top, we go down to the bottom. They can be very basic and plain. They can get a little bit fancy, or they can get very fancy. But these are, for load path, very simple. We would have pin reaction, roller reaction, and the big thing we're worried about is headroom here and meeting our riser and tread dimension criteria, but that's set by the architect. Exit stairs. Exit stairs usually aren't as pretty. They're often tucked in a back room. They can be outside. If they're outside, maybe you have the opportunity to start to get really beautiful with them. You can really see basic stair construction here. We've got our channels turned outwards. This was probably a metal pan with a concrete infill, a metal backer, and then they've put a finish on that, whether it's like a rubber surface or not, I'm not sure. You can see this one looks like it's painted over. So I'm not sure if they put concrete in the pan or not here. You can normally tell if it's a concrete stair versus a steel stair. Steel stair, if you do a heel drop, you'll feel the vibration more than if it's a concrete stair. When you do a heel drop on a concrete stair, you will feel very little. So these are scissor stairs. So they're two vertical egresses on one footprint point. So different floors will have their doors in different locations. So different floors will have their doorways either in different locations, or you can, I always get this backwards. Anyway, you can see that there's two stairs on one footprint. I'm trying to remember, there was something I was thinking about last night that I wanted to say about scissor stairs. Anyway, it's eluding me now. Anyway, you can see here that for this stair, this floor you access over here, this floor you access over here, this floor you access over here, and this floor you access over here. For the other scissor stair, your doors switch locations, or your access points switch locations. This is great because you get two stairs in one location. The problem is that might meet all of your criteria for getting people out of the building, but there's often usually criteria that you have to have them be within a certain distance of points within the building. So you might get your two means of egress here, but they might not be far enough away from every point in the building. Switchback stairs. This is a switchback stair where it's been supported at the landing. So you can see you come down and you switch back and you go past yourself or someone else coming down the stairs. These ones are supported at the landing. You can see all of these have support. This one's supported on the wall. This one, they didn't want to connect to this beautiful old brick, so they inserted steel columns here. This is a switchback cantilevered, and due to Dave's beautiful drawings, we can see that we have an unsupported location here, and Dave has taken the time to draw what is happening within the building here, or in the stair here. Now look at this. We can see, and you can imagine that standing on that, if you move off to the side, you can imagine your stair wants to rack a little bit, which means we can't release that lateral force in our stairs. We cannot allow it to be a roller at the base because we need to be able to resist that tendency to want to rack our stairs. And so if we're doing that, we have to have it pinned, which means we're going to have some forces locked into place. And this is how we can end up with very large reactions at our bases. You're saying something. I can see you want to say something.
Yeah, I'm going to lean in here. the way it was explained to me one time, which was extremely
Would you like
useful.
me to move over?
No, I'm good. Is imagine this as a load path. Diagonal here to that point, diagonal up here to this point. That now is a 3-pinned arch. We have a fixed point, we have a fixed point, and we have a supported point right there. So this point right here is fixed in space by a 3-pinned arch. Everything else is derived from that. So now we have a landing that has to cantilever both ways, tending to work as a teeter-totter. You can't support a landing on a single point, so something has to take out the imbalance. It's torsion in here and torsion in here that take out the imbalance in the landing. This moment here results from the fact that the net reaction is right on the edge. So it's not here in the middle. So if we translate it to the middle, we need to add a moment. But in fact, the resultant is right here on the edge. And this is a similar situation with the steel stair. Once again, we wind up having a diagonal load path, a point fixed in space right here, and a diagonal load path, and everything else kind of falls out of that.
It's funny, I didn't realize you were drawing concrete and steel separately. I thought you were showing how it functions here and then showing how it results. Because that's really what it is that the steel follows, you can visibly see everywhere you need something to resolve all these forces. Concrete, it kind of just gets lost within it. So I thought he was drawing kind of the loads hidden within it.
Right.
And then here in the other one, you were pulling them out and isolating them.
Yeah.
Resolving your couple.
Well.
Regardless, this shows a person kind of standing out here. I don't remember talking about serviceability criteria. Oh, in vibration, I kind of glossed over it very quickly. There was a load case that I said, or if you look at it, it says 1 kilonewton causing less than 1 millimeter of deflection is a very handy load case. We also remember that 1 kilonewton, when in doubt, is a really good load case to use to test things out. Because, and we're going to see next week, that is specified in the code. A person doing something can't do more than 1 kilonewton's worth of damage, according to the code. We factor it for strength. So I will often test things out with a 1 kilonewton point load in various locations. And so Dave's kind of free body diagram here of P out here is typically 1 kilonewton. So you can imagine a person standing out on the very tip of this unsupported switchback or a cantilevered switchback stair. And I'll show you kind of the process of one that I've done in a little while. So here is a switchback stair that doesn't switch back past itself. It goes off in the other direction. And here's a switchback that comes right past itself. Spiral stairs. Spiral stairs you can have as 1 curved stringer and 1 central post. Essentially what we're saying is our inner stringer has curled in so tight it's acting as a post. So as you can imagine, as you curve your stair and as your curve gets tighter and tighter and tighter, that inner stringer becomes a single post. And if you think about that, if that single post could be down the middle, and you can see how all of these are connected to the post. This one we have an outer stringer and a post in the middle. That is the principle that's working with this one, except the weight of the one above is what's holding it in place. Now, I actually believe they cored this and slotted it down over a steel pipe, but the line of support is centered right through all of that. I love this. I think it's gorgeous. So here is one where they haven't tightened it quite as much. So some people call these circular stairs because they're not curved so tight that they're a spiral with only one stringer, or the center stringer becoming a post. But you can imagine this one is pretty darn close to being a post. The tighter it curves in, the more like a post it is. This one, you think, oh, well, they only have the center one. There is no curved stringer as the outer post. And you're right, but look what they've done. They've added hangers for each tread from a beam above. Here they have one center spline that's spiraled, and they've cantilevered the stairs off of it. And Dave is going to go through a lot of these, kind of talking about them. This is just to more show you the types of stairs that can exist. We can do ones where we cantilever the treads and we just simply embed them in the concrete or wood. There is a lot going on in the walls here. I believe Dave will talk about that in some of the photos later on. So I'm just going to gloss over the cantilever treads and I'll let you tell some of your stories. Because I think it was the house you did for Kevin that had the vibration issues. Was that the one?
It had a great cantilever tread. I'm not sure that had vibration issues.
There's one that had, anyway, I'll let you tell those stories.
The one we did for Vera Zek. Or for Vera Straka.
Oh, the teacher at Ryerson.
Yeah.
Right. So this one's really cool, the Le Pere stair. It is alternating treads. Once you're walking up a stair, now, if I'm carrying something heavy or if I've hurt myself, which is often, you'll go up the stairs like this. But most of the time, you go up the stairs with alternating steps. That is the principle behind these stairs. And if you do that, you don't need each tread to be accessible to each foot, which means you can narrow the dimension or the floor space that your stair takes up. So you can see instead of coming all the way out here, this is pulled back to here. So you have to be consistent on what foot takes you up. They're very steep. If you fall, it would not be fun. But for small houses, this is something that's a thought process. I don't believe they meet any codes ever. That's my understanding. That's your understanding too, right? Like, there's like a very narrow criteria when you can build a Le Pere stair.
Yeah, it can't be a public stair. It's got to be an access stair to there, and like an attic or something.
Yeah.
Like anywhere you can use a ladder, I think you can. Yeah.
So it's technically categorized in the ladder requirement, which you can see here. Literally, they're doing that. But it's not meant to be a main stair. We were going to do this in our old house, our little tiny little shack, to get up to our attic. This one's really cool. I like this one. They've actually built it in to the feature elements up to their loft. All right, so I'm going to go through some projects that I've done with some stairs and kind of give you some background and some information on it. And then Dave will go through and talking about some of the pictures. So the very first one is the Senate building that I did with Diamond and Schmidt and a local architectural firm in Ottawa. They had an engineer for the base building, but they did hire me to do all the feature elements. So Diamond and Schmidt came to me to do all of the feature elements within the building. So there was stairs, there was like 10 different types of guards, because if you've seen images of the Senate building or inside the Senate room itself, they have tiered seatings, they have visitor galleries, and those all have various types of guards going around them. They had a door entryway that actually needed to meet some blast requirements. We also had neat signs kind of cantilevered up off the ground, solid stone signs cantilevered up off the ground. So lots of cool stuff happening in this building. This was my set of drawings. This is an image from my set of drawings. You can see that I have treads indicated with moment connections into my stringers. We need it moment connected this way, but we also need each one moment connected this way. That's to help prevent our stringers from racking too much. It makes it one system. You can see that I had concrete on metal deck. My treads are channels on flat, so they were like this and then filled with concrete, and they had a topping going on it, or finishes. I can't zoom in on this, but I actually had to create built up sections here. Often public stairs, you can imagine this is the most public-y of public stairs. And this is the one where I was given the criteria that they would be doing a lot of photo shoots on these stairs. You can imagine all the senators, I mean, it came out just before COVID, so that hasn't happened quite so much. You can imagine all of the senators gathered on the stairs having their photo taken. So that was really kind of the idea behind this. What else do we have here? So forces at the beam for stringer. I'm going to come in close and read because my eyes are getting bad. Gravity, 130 kilonewtons, parallel to 2D. So the force in this direction is 195 kilonewtons. Parallel to U was 10. So my thrust on this stair is 195 kilonewtons. That is a gigantic force. This could not be pinned roller because it is a cantilevered switchback. We are resisting our couples through that top and bottom action. So we couldn't do pin roller, which means we have to develop all the thrust force. This is a heavy stair because it's covered in concrete, and it's in Ottawa, which has a very high seismic zone criteria. So seismic forces govern this in combination with gravity loads. So we have our gravity loads causing a large thrust, and then we have the seismic loads also causing a large thrust. So we have very large forces here. Luckily, this platform was very, very strong. When I did an analysis of this beam, it was only using about 60% of the capacity it had available to us. So you remember how our factored loads need to be less than our capacity? Well, it was about 60% less than our capacity. So there was lots of load left. The stair only added about 5 to 10% on that. So that stair, that beam that's supporting our stair was very, very comfortable. I got involved in this project well after the contract documents were already issued. So some of the problem is it was an existing building. Then they already had the drawings tendered and construction had begun on the renovations to the building. And they were building it in real time. So sometimes I'd be directed to come up with a design for something, and while I designed it, they'd build something else that changed the design. This was at the base. So at the base, so you can see that here we're showing the upper floor coming down the stairs, our landing, and going down, and then the stair cuts off. Here is the bottom of the stair. We have our very large thrust here. We have 195 kilonewtons thrusting parallel to 2D, so trying to kick out this way. Normally I probably would have put a footing there and dealt with it. We had two problems. We were on existing substrate, so they were already at it. There was an old building there, So the foundations already had to go down very deep for anything new they were doing. They had already tendered those, and they were putting a duct here. So this is so they had a duct that was then being encased in concrete for I think it was all the fiber optic stuff. There might have been a power line in there as well of some sort. So you can see on U just south of 2D. So you can see right where my stair wants to come down, there's a duct bank right under our stair. So it was like this, maybe a bit farther, somewhere below our stair. So we couldn't put a foundation there. Even if we could have supported it, it would have crushed the duct bank, and we don't want to do that. So I had to come up with a method of putting 3 small supports, building a steel frame above it, but don't forget we had that very large 195 kilonewton load thrusting along this. So we also then needed to prove that this being cast into the concrete could develop the friction required, that we didn't actually just pull the whole floor slab and damage the floor slab in the event of an earthquake. So let's take a look. I thought I had, I don't have a detail of that. Anyway, we had this piece of steel cast in. I'm gonna add that slide just because it's really cool. I don't know what slide I'm on. Find one that's 32. So literally it was just a big thick steel plate. What do I have it? What size is that plate? Yeah, it is 3.5 inches thick by 10 inches wide, welded to plates on caissons. So this is just a big steel plate frame to develop the gravity loads and our thrust loads. Oh yeah, would you pour that one out? And it's 5:30 and I still have to film another 3-hour lecture today and go for my run, and then I can start my work day after I do all of that. So it's gonna be a long day. So let's take a look at the load cases that I used for this. This one was interesting because we had some handrails that were just handrails and not guards. So they were not preventing someone from falling off the side of something. They were freestanding from the guards. So for a lot of the kind of low-level feature elements within this building, they had spots where they'd have 2 or 3 stairs. So not a fall hazard, but they needed a handrail. And so you can imagine a handrail, you'll pull yourself up sometimes. So dead loads. We had the concrete that was in the pans and the landing, the steel itself. All of that stair is clad in stone. Top, sides, bottom was all clad in stone. And then we had some miscellaneous because they actually had to have sprinklers running underneath it. They had carpet on top of it. So there were some other dead loads. The landing, very, very similar. They just had less stone on it because they had more concrete topping. Live loads. The treads in the landing, 4.8 kPa, what I've talked about. And then here you can see we have the guards and the handrails broken down. That we'll jump into next week. And I think I actually come back to this exact stair to talk about guards. So I do this same process where I show you kind of the design process within the guard for this stair as well. In spite of having this stone allowance on this particular project, they kept making substitutions, and they got very, very paranoid that they were going over these allowances. So finally, while they had already built it, they had already put the stone on, and they wanted a memo for me saying it was okay. Well, that's not really how it works. The contract documents are the thing that says it's okay. And a memo can kind of get lost in the world. So because, as you can imagine, it was a very bureaucratic process for a project like this, dealing with like government, existing building that bought it from another level of government, local engineers, heritage engineers, our local architect, and then me being then a sub-engineer within that, we just decided, let's just explicitly state what the stone accounted for in that stone allowance. So here's my model. Now, remember, there is a strength model and a vibration model quite often. You can see that I have it up here, coming down. You can see I've got my guards modeled in. Sometimes they help, sometimes we use them for strength, sometimes we can't. It depends on what they're doing. They have to be able to work for the loads if we're using them. So this is kind of an extruded version of it. My modeling software is line-based or plate-based. It doesn't have dimension to it. You can visually, graphically give it dimension. It's not very good. You can see even you can see graphically. It's not meant to be a graphic software. It's meant to be a load analysis software. So this just helps us produce some images sometimes. So here you can see it as the isolated elements. You can see my plates in the ground. Here you can see it as the reactions. So you can see I've got that thrust. It says 200 here, and my drawing said 195. They had made some changes well after we issued the drawings. So some of this was about the stone changes. Now you're thinking, your drawing said 195, this is 200. Let's just take a look at that. 195 divided by 200 divided by 195. I am at 103% of the capacity. Is my factored load less than my capacity? Yes. And remember I was like, don't ever go over it, don't ever go over it. Well, I know that we have some things in this that were overestimated. The miscellaneous dead loads on this, for example, overestimated. That I am comfortable, I'm using my engineering judgment, that being over that 2% is okay. And that's pretty common. Engineers will do something like that a lot. It's about knowing what the element is and what it's doing. If I had a column that was governed by slenderness or in a slender zone, I tend to keep it at about 70% of capacity. If it's something that has multiple load paths, I sometimes might even go as high as 110% of its capacity. So I'm going to apologize. It's also recycling day, of course. So Dave is now working on, or not recycling, it's garbage day. Ours is all on the same day. So Dave is now also in the process of taking the garbage out. I mean, he promised me a coffee and I don't see my coffee. The service here. So you can see our very high reactions because we needed this to be pinned. We couldn't do a pinned roller. If we did a pinned roller here, this would kick out this way and this way. So it would shoot this way and this way. We would get movements of like a meter down here. And obviously that is unacceptable. So we had to restrain it. What did our stringer look like? Well, we had our outer stringer, which let's just go back and look at these loads for a second. Look at this, 18 kilonewtons, 153 kilonewtons. Our outer stringer isn't working quite as hard as our inner stringer is. So our outer stringer is this built up section, and our inner stringer, we have a lot more going on with it. We have a very large HSS. This one is built up because they were cladding it in bronze and they wanted this reveal here. They could have used an HSS, but they also needed this kick plate to support their glass shoe. So this is a glass guard on the outside and they needed something to support this shoe and have a kick plate too. So they needed to be able to fasten this. So this system allowed them to put all of those things together. During the construction process, the shop drawings I got were an HSS without this plate. And I was like, nope, that doesn't meet it. A, because you haven't met the strength capacity of what I've drawn here. You haven't met the stiffness capacity of what I've drawn here. And you haven't met the architectural requirements that I've drawn here. So I knew that the architect had a vested interest in what this profile looked like. So there was back and forth on this. Once they met the strength and stiffness criteria of this profile, the architect made some concessions about what the profile looked like. So there was back and forth there. Here is our stringer. You can see the profile of our channel as our tread filled with concrete. And then you can see I've dashed the stone around it to kind of give some imagery of what is going on. This is what I consider as existing because it was designed by someone else and fastening what I'm designing to it. Look at me. Shannon last year was so smart. Here is my duct bank detail. So you can see that we have our duct bank under here, our steel plate built up, cast into caissons. This whole system grabs the slab and prevents it from sliding along. So you can see why I couldn't support my stair right here. In fact, I believe we provided kind of almost a spongy layer under there in the end as well. They got very worried that any deflection here would have an impact on this. We were able to say how little that deflection was, but there was lots of conversations about the impact of this stair being right above this duct bank. Here it is under construction. When this was being built, probably right around this stage, might have been even before this stage. I don't even think they had all of these treads fully welded in. I got a call from the site. People were angry, saying this thing is moving all over the place. It moves inches. So you can imagine that's like a nauseating feeling, thinking you've completely effed up the design. So I went back, I analyzed it every which way. I could only see less than a millimeter of movement, no matter what they did. One thing we determined is that that they hadn't fully welded all of these in yet. So those needed to be welded in to help prevent it wanting to rack. Once that went in, the overall deflection panic stopped. But now they were aware of it. And once somebody's aware of it, you can't be unaware of it. It's like a song that you hear. You're fine never thinking about it, but once you hear it, it's stuck in your head. So I got a call saying that when they stand here on the corner, this moves. Again, I went through it. They said it vibrated too. So I went through, looked at all the analysis. It met all of the criteria. One of the things about vibration is we get to account for the finishes. So I pointed out that they didn't have their guardrails on. So the guardrails will help prevent vibration. They didn't have their concrete in the pans or in the landing. That is huge with adding in the concrete. And then they were going to also have the stone on it. And the stone is huge for vibration. Then they also said that there was a lateral vibration issue. So the stair was vibrating when somebody was walking down it. The stair was vibrating, not this way, but this way. So I was again like, one of the ways to judge it is a 1 kilonewton load with 1 millimeter of movement. I also had done a vibration analysis, and so I was comfortable with that. Now, that vibration analysis, there isn't anywhere in there for lateral vibration issues. So I kind of had to extrapolate a little bit. I had to pretend my stair was tilted up this way and then analyze it kind of going from the other direction and get its natural frequency under 1 kilonewton of lateral load, which a person walking down this way does not cause 1 kilonewton of thrust that way. Anyway, we went through it. The contractor on site said it was moving like an inch. So I said, all right, movement is relative. People, once they're aware of it, think it's something very large. So I said, come out to this corner, tie a platform off onto it, and put sandbags on it. So a sandbag is 66 pounds, so 225 divided by 66, it's 3.4 sandbags. I said put 5 sandbags on a platform hung off of this spot. We actually ended up, I realized that was silly because we could just pile up 5 sandbags right here on the corner. So I like immediately retracted that and I said, okay, rather than hang something, let's just pile up 5 sandbags right here in the corner. So everybody went to site, and I'm talking to them on the phone, and one guy, I think his name was Mike. Mike's like, oh, I weigh 250 pounds, and a kilonewton is 225 pounds. So we got Mike to go stand here on the corner. Well, first they hung a string with a plumb bob and cut it off so that it was perfectly on the ground. We then had Mike go stand on the corner, and we saw how much the string shortened, or basically how much string pooled up on the ground. You couldn't measure it. It was less than a millimeter with Mike standing on that corner. We then got Mike to do a heel drop with someone else standing over here. And remember, this is still even before we put the stone on. And the person over here felt it for less than a second. They could feel it, but it was like a tiny little imperceptible sense of vibration. Everyone acknowledged that the stone was going to go on it and would just improve it once I told them that that was how it works. And then once they put the railing on, it would get even better. Everyone was fine with it. It just disappeared. I have never heard anything else from site about that stair. In the end, what was on the drawings was fine. 0 changes were made. But there was, gosh, I think I wrote 7 memos and like 3 different testing procedures on what they could do to prove this. And a couple sleepless nights because they had me in a panic. Somebody tells me my stair doesn't work. My gut instinct is to believe them. So here it is with the glass railing, or the glass guard going in, and then you can see the handrail behind it. And here it is with the stone and its fancy red carpet, looking out into Ottawa, and you can see how this is going to be a great place to do photo shoots. Okay, I am taking longer than I meant to, because we all know how long Dave talks. So I want to get to the point that he'll have his beautiful pictures to go through. So this is in a residential home. This is with Williamson Inc. I spoke to them at length about vibration. Now, for a stair this tight in curvature, for the height that it's going down, vibration isn't often going to be an issue. I talked to them about the cost and the merit of doing a vibration analysis, and they had an owner client who was comfortable not pursuing vibration design. They took my word that we would do the nominal checks, which is the 1 kilonewton should cause less than 1 millimeter of deflection. And they said if we feel a little bit of vibration, that's fine. It was an older couple, and one of the gentleman's mother was also living with them in the residence. So they don't anticipate somebody running up the stairs while they're walking up the stairs. If it was, I've also done a stair with Williamson where the owner had 3 boys. They were aged like 8 to 12. And there, you can imagine vibration criteria was imperative. Seeing how my kids treat stairs and the amount of times I yell, "Don't run on the stairs!" You can imagine in that situation, vibration was critical. This one, they said we do the nominal checks and don't go too in depth with the vibration design. This was a really, really cool project. This is one where we had the builder on board very early, which is really helpful for something like this, because there's back and forth. There are 100 ways to build all of these, and I'm trying to anticipate what way that particular fabricator will like to do it. If you already have a fabricator on board, you can talk about it, and you can work out what is best for them while still meeting the architect's desires. So let's see what my loading criteria was. This was very much a residence. So my basic strength load was 1.9 kPa. Yeah, they'll have parties at this house. I missed the opening party, which I've heard was lovely. But I think it was right when I was having Duncan. Like, it was Duncan was like only a couple weeks old. I had wood paneling on everything, so you can see I have the weight of my stringers. I had an E-tabs. I usually track two. This is one for kind of designing just my stringer. Here's the one for my guard. Risers and treads. These were the loads I was putting on it. Because I needed to be applying it as line elements, not as an area, I needed to know what this 1.9 kPa was as a line load, but my tread varied in thickness from being wide at one end to narrow at the other, so I had a varying live load. So it was high at one end and tapered down to a low live load at the inner stringer. So a high live load at the outer stringer, a low load at the inner stringer on each tread. Here was my model. So you can see that it curves around. This one, we were very sensitive to the impact on the existing structure. It was actually Blackwell's office that did the analysis for the base building. So they were the engineers for the base building. And the stair was my scope. And this is one where, again, there was some interesting parts where, because it was a wood building, they were doing a lot of trusses and joists and some proprietary wood elements within the building. So as much as Blackwell was the base building engineer, there was also another engineer, there was shop drawings for some of the elements within the floor as well. So there was communication with Blackwell on what these elements were and what the impact of my loads were on their elements in the building. Because where we provide releases and how we detail how they connect to things can have an impact on where the load goes. Thank you. I finally got my coffee, no tip. So let's see. So you can see that my stair is supported here on this double cantilever, and those elements had posts here. So I wanted to see what impact my stair had on their elements. I was able to reference their drawings and see what values they had on these elements. I actually was able to look at their E-tabs model because I kind of have an inside source. Actually, the person within his office who was working on it was fantastic for communicating with this on as well. So I was able to go directly into their model. That wouldn't normally happen. Normally, there'd be a bit of back and forth, some emails, sharing loads. I was able to go directly into the analysis and take a look at it. So how this was built up, I'm going to disappear from the screen because I did this in 2014, so I need to remember some of the elements. Because this was a unique project, I was able to kind of create the way we presented the material. So I created a series of drawings that indicated how I anticipated this would be built and created. Because not only does it have to work, it has to be buildable. And it has to be able to get into that tight space inside that building and then have those finishes applied. And some of those finishes you want as much applied in the shop as possible. So I came up with my anticipated method of construction. Then the fabricator communicated back what he could do that was slightly different, and then we revised it. But I didn't produce that normal set of drawings that you would typically see. I did image captures and then wrote out instructions about what I thought I'd see. So here's the first one. So step one, this is Peter's scope and the fabrication of the wood stringers. Thickness would be determined by him, but likely 3/4 of an inch. So these were pieces of curved plywood, essentially. So that would be, that was milled and tapered, almost like a jig. So this was kind of the template. This wasn't structural, but would be used as the kind of the basis to build everything else on. Attachment of wood treads and risers. Thickness is currently shown as 3/4 inch. Might need thicker for end screws required to tie steel stringers together. Not shown yet. Would appreciate Peter's comments. So this is where I knew what I needed for strength. He knew what he needed for his fastening that then I would verify, but depending on which wood he was picking and what thickness, the calculations were very different. So I wanted to know what he thought he could, before I went through and did the calculations on a very, very thin one. If he couldn't even work with it, why would I bother with those calculations? Saving the owner money. So I was like, what one can you work with? And I'll start from there doing the calculations. So then, stage 3, attachment of steel stringers to the inside of the wood stringers. So you can see our wood was templated like that, and then this steel gets laminated along the inside. There will be lots of screws. We did end up coming up with a screw pattern for it, but the very first kind of take on how I described it was lots of screws. So that was 1/4 inch by 10.5 inches. So it was just a tiny little thin piece of steel. Remember, thin steel in bending is actually governed by the buckling of the compression side. So you remember, steel isn't great in compression because it likes to buckle if it's thin. And in bending, the top usually is in compression, so it tends to buckle. It's great in tension. If we can prevent something from buckling, we can make use of a lot more of its capacity, and you can get it very thin because we don't care about buckling anymore. We can use strength alone. And that was the idea here. The lots of screws are to prevent the steel from buckling, allowing me to keep it very thin and attach it to the inside of what was the wood template. And then attachment of wood stiffeners. So you can see periodically we had wood stiffeners in there. So those were to assist in vibration, stiffness, and resolve strength forces for the guards. So the guards want to kick out, and that prevents the guards from trying to kick in. Treads and riders are faded and only showing one. So that was just to kind of help illustrate it. So these pieces here were 2x10s. Attachment of wood guard template. So these were 1 inch. These would be 1 inch, Peter, of, so they're 1 inches wide of 3/8 inch plywood at every riser. Space to work for Peter. I had them shown at the riser. And then infilled in between with more plywood. So this one isn't the strength, but this is the one that's helping us template the curve. And then attachment of the structural guard, which is 3 plies of 3/8 inch plywood, curved to fit and fastened to stringer. So they laminated, because it's hard to bend something thick, and this was a tight radius, we needed to bend 3 separate small elements and attach them to this template. And then there's that 4th layer that was our template that was infilled as well, just so that they're veneer on the inside. And then they did a thin veneer inside and out. And this is the resulting look of that. So we have template wood, steel, then we have our guard, 3 layers of 3/8 of an inch plus the template layer. But all together, so what did we have? We had 3 divided by 8 times 4 plus, what was the plus 0.25 plus 3/4 of an inch, so 0.75. So the whole thickness was only 2.5 inches, and that was only down here where the stair was. Up here, we had less than 2 inches at the guard thickness. So it gave them then, I think they did another 3/8 of an inch of their beautiful exposed pieces of plywood, resulting in a very, very, very thin guard. Like I said, the gorgeous pictures. This is just beautiful. All right, Assiniboine. This is another one where bureaucracy can have a big part in governing what we do with our stair. I know if any of you know who Dieter Jansen is, he's an architect in Toronto. He does work with Diamond and Schmidt, so he actually was the Senate stair. He was featured recently in, is it Canadian Architect? Dwell did I believe a thing on his Instagram series called No Stairs Allowed, basically talking about the severe restrictions that codes have placed on stair design, basically that we're now building to the lowest common denominator of human capability of functioning. He's very, very worked up about this. Basically, they're saying that his interpretation of the codes is that it assumes people don't know how to function in real life, and these stairs are to prevent people who would do really dumb things from doing really dumb things, and that maybe people should just do dumb things and they'll realize they shouldn't do dumb things. We shouldn't build our stairs assuming everybody is trying to do really dumb things. I'm not going to weigh in on the merits of that or not. I can comment that some of the latest code requirements are very restrictive on what we can do with stairs. Dave will probably, the last slides that Dave goes through, probably 3 of them would you be able to build now. So Dave is the engineer for all of this beautiful stuff, which is probably one of the most complicated projects, I would say, definitely in Canada and North America. Once this gets kind of published, it's going to be wild. People are going to lose their minds for it. It's been under construction for a while. So they came to me, I was kind of in the thick of kind of communication breakdown between the owner and the contractor and the steel supplier and the engineer and the architect. So basically everybody was mad at everybody. And so they hired me to do the stair. I don't know if they knew I was Dave's wife. The architect certainly did. It was KP&B. They certainly knew I was Dave's wife. I don't know if the contractor and owner did. That we weren't hiding anything. It just never really came up. They must know. They all know. Probably. They must know. So this one, vibration was critical. We don't have concrete on it. We don't have a lot of finishes on it. There's almost, no, there was concrete on it. There was some concrete, but we didn't have all of the finishes and all of the stone like on the Senate building. So vibration was critical on this stair. It also had lots of intriguing criteria for code requirements. So here is my loading chart. So you can see I still literally think about strength, stiffness, vibration. Stability is inherent in building my model. If I've built my model and it flies off into space, it's not stable. So that gets solved within the model. So this is to help track my data for myself. So here is the model for this stair. It is a curved stair, but this doesn't do justice to the size of it. What was the radius on this? 3 meters? 4 meters? The Assiniboine stair. Like the circle, the radius was like 4 meters. Like I think from this inner point to here is 4 meters. So this is a gigantic stair. I hear a thump. We'll wait and see if we hear crying. So this is the model that I built. We have bent metal coming up as the risers and the platform, but they're curved. So how do you bend metal while also trying to meet a curve? This is my analysis. Again, this is one where We can't release the ends as a roller, so we have some embedded forces in this. I needed separate models for strength and stiffness because these, I don't get to use the finishes. For vibration, if I use something in my strength model, I need to make sure it has the strength to resist those loads. I only want in here what I'm engineering and detailing because I need that to work. If something else yields slightly, and yielding can be just the tiniest little bit of release of loads, I know that everything I've designed will work. For vibration though, we assume that this isn't at its maximum loaded case, so all of its full strength load. So those elements that we wouldn't use in strength are there. There's no way they've yielded. They're gonna be there to help perform under vibration criteria. So I needed a model for strength and stiffness. I needed my model for vibration where I get to put in some of the things that might not be in there for strength. And then we had the guard and handrail analysis as well. So this is the stair that we're talking about, and it's installed now, isn't it? Could you finagle me some pictures of that?
Yeah.
The rest of the building isn't built yet, so it's still, it's probably got some hoarding around it, and they're protecting it. But the metal is in, and I've heard nothing about anyone complaining about vibration. Oh, I guess that's all I had on this. I did a very complicated vibration analysis. I don't know where my vibration slide is. I guess once I've shown you what my vibration spreadsheet looks like, it doesn't really matter. We needed to meet all the criteria very carefully. So both the normal one of you walking up the stairs, one of you standing still and someone walking, and one of you standing still and someone running. There was, before I started the analysis, a lot of talk on whether we needed to meet the one of someone running. I felt we very much needed to meet that because I know that if I was here, if I was down here and someone else, a stranger, was standing out here taking a picture and my 3-year-old ran up these stairs, they would cause vibration. Now, my 3-year-old isn't 168 pounds, but imagine then Dave starts chasing them up the stairs. Then we'd be meeting our 168 pounds going up the stairs, causing that vibration load. All right, so this is another switchback stair. This one is a double, like we've got 1, 2, 3 internal landings in this stair. This one was in Hawaii on one of the islands. I can't remember what island, but this is all plate steel. So fully plate steel, nothing else happening on this. Comes up, there's these beautiful kind of notches and carve outs in it, then with the handrail guard on top of it. With this one, we really cared about the internal stresses. So you don't usually break it down as a simple line analysis for this. Strength wise, as a stair, it wasn't so bad. Remember our steel stress is 345 MPa. So we want to make sure any of our stresses, factored stresses, are less than 0.9 of 345. So 0.9 times 345, we've got 310. Actually, it was plate steel, so 0.9 times 350. So 315. We want our internal stresses to be less than 315 MPa. Personally, when I'm doing something like this, I like to keep it less than 200. And what I tend to do is analyze it. And if you have large meshes, it can look like something works. I will do a reasonable mesh. So a mesh is, how small do I break these down? The more you break it down, the longer it takes for the analysis to run. and the more complicated it gets to kind of look and dig into the results. So part of engineering judgment for kind of finite element analysis is this place between too much meshing and not enough meshing. And it's finding that reasonable zone in between and what's a reasonable amount of meshing. So what I did was I did a reasonable mesh everywhere, and then I identified hotspots. So most of this, the stress in the steel, is anywhere between 5 and 50 MPa. Most of it is nominal. You can see right here we have a hotspot. You're on camera, eh?
Just took me my shirt.
Okay. I thought that so, but you are on camera. So we do need to look at this hotspot. So here I zoomed in, and in here we were approaching kind of my criteria of 200 MPa. So I broke it down, and you can see the fine mesh here. We've really broken it down. I want to see, no, we didn't do the next one. What was actually done, so Dave was the engineer for the house for this building, and I was doing actually Blackwell was doing the stair as well. They just hired me because this is my forte. So I was actually working for Blackwell for this stair. And what can help relieve stresses is what gets really bad is where we have a point. What you can do is actually create round holes to relieve stresses. So what they actually did was actually put a hole in there to allow stress relief at that location. We also reinforced around that opening. So we doubled the thickness there, which would have the stresses. And then they also put a stress relief hole. Whenever you're cutting something that has stresses on it, what you want to do is make it round. It's the points that can be a real problem. If you've ever heard the stories about one of the kind of early Boeing 747 stories is they had square windows in the planes, and there was actually a crash. I think more than one, several, because of the stresses in the steel where the glass window intercepted it, and it actually caused catastrophic failure of the plane itself. And so now you'll always see rounded openings in the steel for the windows. Okay, so the next phase is Dave's scope. So these are some that either I or Dave has worked on. Some were just pulled from the internet to allow discussion. Where possible, I've provided who the architect was. Some of them I couldn't find the source information, and I apologize for that, but it's because they're widely available as images on the internet. So it's not about me trying to sneak it in or anything like that. I'm trying to follow all of the proper rules for kind of accreditation or providing the proper credit for things. I've said this before, many of these don't meet our local codes, probably even their local codes. And I've said that the OBC, or the Ontario Building Code, just recently restricted many more items on some of these stairs. So Dave, did you want me to stop this and you can either film it later after the kids go to school and get up, or did you want to just jump into my seat and start going on it right now?
I'll do it, but not right this minute.
Okay,
Give me a few minutes.
so I'll stop it. Dave's gonna come on in a minute. I'll mesh the video so it'll seem seamless to you guys. So now Dave joined us, and he's gonna talk about the stairs.
Do you want to lean in?
Oh, hi. They've just seen me for an hour and 40 minutes. I think they're good. They've probably had enough of me this week. Okay, you might see me running in the background with children, but Dave's got the mic now.
Hi everyone, thanks for indulging us. Of course I have to figure out the tech because my slide is not advancing.
Oh, that's because you're on the wrong screen. Yeah, you have to be on that screen, yeah.
There we are.
It's misleading because you can, for us, we can see our mouse on the recording screen looking like it's on the image capture screen. It's
So these images are from, many of these images are from a lecture that I created 15, maybe 20 years ago. They're still great stairs. They're probably more tectonic than current fashion, or a lot of them are. But many of them are non-compliant now, and many of them were non-compliant at the time. So we're going to change this portion of the lecture to a gallery of non-compliant stairs. But anyway, they're still interesting. They can give you some idea of the types of construction that is possible, and some of the stair forms, and might even introduce you to some aesthetic ideas. I'm going to point out the kind of the most salient portions of each particular stair, and we won't go through the whole thing. But the things that are interesting about this, look at we have steel plate treads and steel plate as the stringer as well. Interestingly, for this portion here, which is the prop, the strut that holds the landing up above, it's a channel. It's stiffened. The reason is that the treads themselves brace the plate against buckling, and so it can be a simple plate. As soon as you're out here and you're in the kind of free air, you can't be so slender. It's carrying compression. It needs to be stiffened with some flanges to keep it from buckling laterally. This is, of course, a stair that would not be permissible in the Ontario Building Code, because it is not only do we have gaps that are larger than the 4-inch ball that is our basic criteria, but are also horizontal, which means that it's a climbable stair.
Just a reminder that next week we're going into guards, so that I haven't talked about the 4-inch
Right.
ball, because that's all in the guards next week.
Got it. So another beautifully minimal stair. I know Shannon was talking about open risers. Open risers will soon be or maybe perhaps are currently not permitted in the National Building Code, because they present a tripping hazard, particularly for people with visual impairments. So open riser may very well be acceptable within a dwelling unit, but not in a public stair. So this is a switchback stair, as you can see, very, very minimal switchback stair. This one has a landing support. There is obviously a valid load path without a landing support, and Shannon talked about that in some detail. So we could do this without a landing support, but look at how long this upper run is. So this is a very high floor-to-floor height, and so this would be a very flexible stair if there wasn't a landing support. So in this particular project, landing support was provided. The other thing that's worth noting here is have a look at this guard. I know Shannon's going to talk about guards, but here we've got a cantilevered glass guard that is embedded in our stringer. So our stringer in this case would have to be a U with very close parallel plates and a closing bottom plate, and the glass just slips down in between those two plates to cantilever up. So very, very clean. The glass doesn't contribute structurally from a strength point of view, but glass in a situation like this is very effective for damping. Shannon talked quite a bit about damping. Damping is one of the things that influences our perception of vibration more than anything else, and yet it's the thing that we have the most trouble quantifying. So if we draw a vibration wave, it's a sine wave like this. There's our neutral position, is the horizontal. I've advanced the slide by accident. My goodness, I went right to the end.
Are they okay?
Oh yeah, but I advanced the slide by accident.
What? Oh no! Don't. Okay. Okay, I have to just. Why did you go right to the end?
I hit something with the pen that just advanced me by mistake.
All the way to the. Okay. Where were you? Here? Had you done these ones?
No, not yet. What?
So this is the first one. Were you on the first one?
Yeah, why don't I just start from there? I'll advance myself to the
Okay.
slide that I want to be on.
Right. It's just that it automatically defaults to these screens, so I have to swap presentation slides and then minimize
Sure.
the viewing screen. So there you go.
Okay, so I'll try and not do that again. So I was just talking about vibration. I'm going to try and be a little more careful this time. And converges, which it will, the ratio of the energy of that wave to the one before, this energy loss is damping. We represent it with a beta. Oh my God, OBS has crashed. What is OBS, John? Yeah, this stupid thing has crashed. And I'm frozen.
Okay, there you go.
Okay, we're back. I'm not going to try and annotate the screen. I think I'm screwing things up by doing that. The point I was making is that damping is critical. Damping is difficult to quantify. So it's easy to quantify the amplitude, it's easy to quantify the frequency of vibration, but very difficult to quantify damping. But we know that it's critical. It has one of the greatest impacts on your perception of vibration. Damping is the energy lost from one wave cycle to the other. And it's usually expressed as a percentage. So 2% damping might be representative. That means that each cycle of vibration is 2% less than the previous cycle of vibration. Introducing glass handrails in a shoe introduces damping because the glass itself is effectively perfectly rigid. The steel stringer is not as rigid as the glass, which means that the steel stringer is trying to sag while the glass is trying to remain rigid, and the glass will slip within the shoe a little bit. And that slip creates friction that absorbs energy and gives us damping. So we have had difficult discussions with glass people who said, no, our glass cannot be part of the load path, and we've had to explain we're not counting on it as part of the load path. We just know it's going to damp the vibration. It's not going to reduce amplitude. It is not going to increase frequency. It is not contributing to strength. It's just absorbing energy as it slips within its shoe. This is an interesting stair from British Council offices in Spain. You can see an expanded metal within a frame for the treads and landings, and a double plate stringer, very, very narrow. So the reason it's a double is because if it was a single, it would be a teeter-totter, right? So we make it a double stringer, and now as you load the tip, you push down on one, you pull up on the other. So a very similar strategy. The canopy outside the Fields Institute, right next door to 230 College, the old architecture building, used a similar strategy. Very tectonic, very industrial stair. So this one has a channel that is under the treads. The treads sit on top, or maybe it's a wide flange beam. The treads sit on top, and it looks like a tension rod in the guard. Again, climbable, open riser, not a contemporary stair, but a very, very clean, simple design. This is one that I did that I'm particularly proud of. I did this years and years ago. It's a glue lam stair. with a switchback. And so it was a challenge to, glue-lam. Steel is very easy to bend it. We can put a full moment connection as we translate our way from the stringer into the landing. There's no problem having continuity in that joint. We can't do that with wood. Wood has to be straight elements. So what we did here is the outer stringer extended past and was supported. Similarly, the outer stringer on this side extended past and was supported. So these two channels carry those two outer stringers. We have a header between the outer stringers, and the inner stringers are supported by the header. So I think it was a clever arrangement to create a switchback stair with wood. The other thing that's interesting here, wood connections are notoriously bad, they're just not very strong. Wood is weak in the direction perpendicular to grain, and connections are generally governed by the perpendicular to grain strength of the material. So wood is extremely strong parallel to grain, weak perp, and that's what governs the connections. The architect did not want to see gigantic connection plates for the guards, but guard forces are very high. So what we did here is we took a pipe, 90-degree bend with a full moment connection, a small escutcheon plate right there on the outside, just very nominal, and we connected that to the guard on the other side. Here we've got a right-hand thread, left-hand thread, so that we could tighten that little link and draw the two threads to the two guard pickets together. Shiguro Bond stair. This is the magic stair. So what we've got here is a cut plate stringer spanning that whole distance. I'm still not convinced that there aren't hangers that have been photoshopped out of this. Certainly that one's a hanger, and so that creates some fixity here. This stair would be extremely flexible. We get a call one time from somebody who was designing a condo, and they said, hey, we saw this stair, we love it, we want a stair just like that. I did the calculation and found that if the stringer was 60 millimeters thick, it would deflect 200 millimeters at mid-span. It's so flexible. So what we did in that case is it was strong enough, it was just so flexible. We had them cut the plate on an arc, pre-cambered. So we derived a cambered shape, and then at mid-span we had tension rods, and we preloaded it down. So you weren't aware of the fact they were tension rods, so they're very, very small. You didn't perceive them as supports, and from a strength point of view they weren't, but from a stiffness and vibration point of view they acted as supports. They had the same impact, so that it became a rigid stair. This is a stair that we did with Giannone Petriconi many years ago, which it's an unfortunate image because it doesn't really do justice to the stair. So this stringer is very, very long span, single stringer. It does not connect to the wall on this side. So when you walk up the stair, you're actually aware of a roughly 4-inch gap. The stair is completely floating. The treads cantilevering out of the stringer. You can see the glass guard disappearing into the stringer. The stringer was made actually with a pair of channels, 300 or 360 deep channels. Flanges oriented towards each other, closer plate on the bottom, closer plate halfway, and the glass slipping down in between. Okay, this is one of my absolute favorites. Not because I actually think it's all that beautiful. It's fine, but from a structural behavior point of view, it is so clever. This was structurally engineered by my pal Guy Nordenson from New York. Now, let me see if I have a diagram. Yeah. No, I don't have a diagram. Damn it. Okay, so let me explain how this one works. Obviously we can't cantilever a tread out of a piece of glass. Whatever moment there is in that tread has to get transferred into the glass, and the glass can't take it. The glass is not weak or is not strong enough out of plane to resist the cantilevered forces. And yet here we are, we're cantilevering treads out of glass. What the glass is really strong in is in-plane forces, or in-plane strength. So each of these cantilevered treads is supported on the one below. We've got this cascading of load down the stair. So how does that work? We have a cantilevered tread. It's supported on this side. We have load coming down from the tread above on this side. And that's causing it to rotate. If we support it here and load it here, it's trying to rotate like this. That rotation is in the plane of the glass. So these are closed sections to make them torsionally rigid and connected back to the glass to take the in-plane force. So load cascades down the stairs, the glass takes the in-plane force. I don't know if the guard is actually contributing here as well or not, but we can see this, the tension cables in between. My suspicion is the guard is doing enough without assisting in carrying the stair, because there are no pickets all the way along. That guard has to span right from end to end. So the structural I want to say mechanism, except that it's not a mechanism. It's exactly the opposite of a mechanism. A mechanism is something that moves. Structures don't. Structures are static. But the structural load path for the previous stair is the same load path. It's the same system that we would see in cantilevered stone stairs. So the stone stair gets some embedment into the masonry wall. So in fact, there is a bit of flexural resistance, but not enough. If these were not connected to each other, these would break. But the stone stairs are torsionally rigid. And you can see that each one is connected to the one below, so that we do get this cascading of load down the stair with that torsion taken back into the masonry wall. This is a very simple, very tectonic cantilevered stair with these little tiny trusses cantilevering out of a concrete wall. This is one that I did 30 years ago, I think. I mean, very, very long time ago. Third uncle. They were so young at the time. We were all in our early 20s trying to figure this out. But a wonderful stair. They wanted a cantilevered wood stair using reclaimed wood, cantilevering out of a wall. There was a block wall. I knew that the block couldn't take the forces. We had no way of connecting wood for big moments like that, and yet this was their objective. What we did, here's your block wall here. We built a stud wall right in front of it, but the stud wall stops at the end of the side of the stair. So we cantilever out the stair, we prop it on the stud wall, and we use the block to hold down the back span. So what we're doing is cantilevering through a double wall here. It worked well. I mean, they were very happy with it. And we never got any callback or any complaint. I think because it was reclaimed lumber. So here's the problem. Something like this, you've got this very short lever arm. You've got wood that from green to fully seasoned will shrink by 1/4 of an inch in a foot. Even if you get nice dry wood, it's going to shrink by 1/8 of an inch in a foot. It shrinks a lot perpendicular to grain. Our lever arm is maybe a foot, which means that we're going to see a rotation in that tread, if we were using normal lumber, of something like 1/8 of an inch and a foot, which translates into 3/4 of an inch. No, not 3/4 of an inch, but 1/2 an inch by the time we get to the tip of the tread. So a significant sag in that stair just due to the seasoning of the lumber. Fortunately, they used reclaimed lumber. That's just what they had and what they wanted to use. It turned out to be the important thing that made that stair actually work. Hi, Malcolm. Val, you want to say hello to the students?
Hi. He very much wanted to hug you, and he was pretty sad that he didn't get his morning snuggles.
My guy. They're my favorite.
Come on, let's let Daddy finish teaching and I'll get you your breakfast.
So here's another cantilever tread stair. These ones, I told you that the previous stair wouldn't have worked because the wood wasn't strong enough, and here I'm showing you one where it clearly does work. But whereas the previous one was crappy old spruce, these ones would be hardwoods and would have been much stronger. So cantilever out of wall, probably using a very similar technique to cantilever the treads. This is one that I did with Kevin Weiss from, it was Weiss Bow now at the time, now it's Weiss AU for Weiss Architecture and Urbanism. Kevin wanted cantilever treads and was pouring a big, beautiful architectural concrete wall. What we suggested that he do is core drill. So pour the wall. We're not going to put cast-in plates. We're going to pour a really clean wall, and we're going to core drill into that wall pairs of holes into which we could slot and epoxy a pair of pipes. So each one of these treads is a millwork box that's designed to slip over a pair of pipes which cantilever out of the wall. Into the end of each of these pairs of pipes is a steel box. So there's a welded steel box, and into the welded steel box we can slide a piece of glass which can cantilever up. So this does a bunch of the things that we need guards to do. It cantilevers up, it's strong enough. It's got the gap is limited to 4 inches, which satisfies the minimum or the maximum gap criteria. What this stair does not have is a connecting rail at the top, which is mandatory under the building code, but somehow we got away with it. The other thing that we don't have here is a handrail. This just happened to be photographed before the handrail went in. There was a handrail that was installed along the concrete wall after the fact. But it was so beautiful without the handrail that it was photographed first. Expanded metal stair, single stringer doing most of the work down the middle. And a folded steel and wood stair. You can see the stringer in the middle on this one as well. Trying to express that thin edge of the stair means you've got to pull the structure in from the edge, but the structure still has to be there. So this is probably a hollow steel section down there in the middle. Supported on a single point, which suggests that the torsion in that hollow steel section is taken into the ends. Another stair that wants to celebrate the fold. To do this in concrete is a real challenge.
Duncan needed to say hi now too.
Hi, Duncan. I love you, my boy. Okay, give me a big hug. Big hug.
My arm is stuck in the middle of this hug.
Okay.
All right, you nuts. Come on, Malcolm, come with me. Let's go get you breakfast. Come on.
So doing this in concrete is a challenge. And the reason it's a challenge is that we need, it's not that the concrete's not strong enough. So if we look at the thickness here, it's it's maybe 6 inches, 150 millimeters thick. We know that the depth to span ratio for concrete is around 20:1, which means we can go almost 3 meters with 150 millimeter thickness. That's not a problem. This may be pushing a little bit, but not too much. The challenge is that we've got to bend our bars. We need that full 150 millimeter thickness. We can't run a single bar, straight bar up the middle, because then our thickness is measured across the diagonal from the inside to the inside corner, and suddenly we've got very, very little thickness. So the challenge in a folded stair like this is how do you get the rebar exactly where you need it so that you know that you've got the strength? My suspicion is that recessed well back underneath is actually a support, so that it has the illusion of a folded plate spanning that way, but in fact it's cantilevered out of a center support. So here's another trick. So we've got this very thin edge here, which of course is inadequate to span the length of this. But by curving the bottom in the middle, we wind up with a net section that's a straight run. So within the volume of that stair, because it's straight on top and curved in the bottom, we have a strong enough beam running down the middle to span from end to end, while still giving us that really thin profile on the edge. I know Shannon's going to talk about guards, but look at this detail here. So once again, here's an architect did not want to see a big bolt plate, but guard forces are very high.
A lot of these slides, Dave, are in a lot of these images.
Right.
Are the ones in the guard lectures.
So in this case, the architect knifed the steel into the side of the concrete, and the anchorage would have happened inside the concrete, not on the face. Problematic from a sequencing point of view. This doesn't fall into the normal workflow. Normally the concrete is cast and the metals come in afterwards. So this needs real commitment and coordination. That's slightly unusual. So here's a spiral stair. There are spiral stairs that are off-the-shelf products, where each cantilever tread is welded to a piece of pipe, and they stack one above the other, probably with a column down the middle. And so we can see that here, that we can see these sections of pipe with the cantilever treads. Palm House and Kew Gardens. Again, this is a spiral stair cantilevered off a center mast. Okay, this is in Sagrada Familia in Barcelona. Spiral stair cantilevering out of a stone wall. Now, the one thing I did not mention, and I'll talk about this in a minute, is that a spiral, while it's a ruled surface, is also anticlastic. Anticlastic means that we have a concave or a convex curve in one direction, concave in the other, and there is some shell behavior in the spiral. So in this case, the stone was cantilevered out of the perimeter walls, but in fact there is a valid load path even without that. So Eva Urikna, her stairs are extraordinarily tectonic, very, very fine, largely tensile. But look at the center spine here, cut out of a piece of pipe, doing only as much as it absolutely needed to. The perimeter guard acting as a big truss with all the diagonals. Really challenging to do things this fine because there are compression elements within this. It's of a scale where it looks like every single piece is in tension, but it can't be. There are compression elements within this, and they're just refined to that extent that they can be extraordinarily fine. This is a key clamp stair, or Alvin Industrial. These are manufactured fittings. Now this is an extraordinary laminated steel plate stair that Yawlis did for the CIBC Banking Pavilion in Montreal. So each of these plates is cold warped into shape. I believe that they were 6 millimeters by 25 millimeters, maybe, plates, and laminated together to create a surface. This was done without the benefit of computer analysis. So they scale modeled this. Rolly Bergman figured this out by hand. They built and measured a scale model and extrapolated the performance of this stair. It's absolutely extraordinary. And this is where I was saying, here we've got a spiral stair. It doesn't have a central column. And these plates are much, much too shallow to span the length of that stair. What makes this work is that a planar spiral is actually anticlastic, and so it's behaving as a shell. I'm baffled by this stair to this day. It's amazing. Another beautiful stair that's a little bit simpler. This one is a very simple concrete stair, center core, and a perimeter guard element. That's the perimeter guard that's acting as a structural stringer on the outside. IMP stair in the Louvre. So this is interesting. So again, this is a stair that wanted a very, very fine reed around the perimeter so that it looked like a ribbon, and yet obviously that is not adequate structurally. So a large torsion element can be built on the inside. So you fake it. You put all your mass to the inside. You make it very, very thin on the outside so it reads like a ribbon. And so this stair is cantilevering out of a big torsion box along the inside stringer. Tension net staircase. So instead of having a center column, we have a central tension net. So these are compression rings, which is what gives it this kind of rotated lenticular shape. And they're in compression, but they're very small, so they can be very fine. And then the rest of it is tensioned. There's an interesting, I alluded to this before, but we can actually use tension elements to carry compression, which sounds extremely weird. But imagine that we've got 1 kilonewton of compression load. Well, if we put a cable underneath that, the cable's obviously going to buckle. But what if we take that cable and we stretch it and we tension it? How am I going to get into here? We tension that cable with 2 kilonewtons of tension load. Now we put our 1 kilonewton of compression load on, and what do we wind up with? Well, we wind up with 1 kilonewton of residual compression on the bottom. So we put 2 kilonewtons of tension, we put a kilonewton downward load on, which would have been in compression, and we have residual tension. So as long as we put more pre-stress than the amount of compression we're anticipating, then we can use a tension element to carry compression. And so that's this central lenticular rotated lens shape. Another spiral stair, cantilever treads with a very thin edge. You can see what they've done here. This is actually a box section down at the bottom. The stringer is a box, then up above is a plate. Now, this is interesting. So a plate structurally cannot carry an awful lot of load, or essentially zero load. Under any kind of compression, a thin plate like that would just buckle. The amplitude of movement associated with vibration is extraordinarily small, which means the stress fluctuations in the system associated with vibration are extraordinarily small. And so even though a plate has effectively no strength, it's not actually zero.
it's near zero, but the stress associated with vibration is also near zero. So that plate, even if it's ineffective for strength, will help us tremendously for vibration. So the suspended glass stair in between two walls. This is not as lovely as the one that Jim Sutcliffe did at the Integral House. Hopefully I've got an image of that. I don't think we do.
Because it's hard to photograph to see what it's doing.
Well, we've got to find some images. As I see some of these precedent images, I realize that there are stairs that we have done since then that are equal to these precedents that I'm. Anyway, so this is a really interesting inverted stair. It's not actually an inverted stair. It's just they've created they've mimicked the treads and risers on the soffit to give the image of an inverted stair. Piece of millwork stair. So we can see that it's been that the millwork for the stair has been incorporated to create bleacher shelves along the sides in a really lovely way. Another piece of millwork that acts as a stair. So Saarinen's General Motors Technical Center in Detroit, this is a suspended stair. Every single tread is hung from above on cables, and these are actually milled stone, if I'm right, so that it gives you the impression you're walking through a waterfall. Another Eva Eurykna stair. We can't even explain this. I skip over these because I can't trace the load path and draw the free body diagram of these incredible tension stairs. So this is a really lovely, interesting stair. It is not entirely clear to me where this stair goes to, but again, very tectonic. You can see this one they've created. So this pipe is obviously too shallow to act as a stringer, and yet they've used it as a stringer by introducing this bowstring truss underneath to stiffen it and flexure. This is a very clever stair going up to a loft. Again, they've created a truss, but it's the treads and risers that form the web of the truss. So we tend to think of riser treads, all orthogonal. Of course, trusses need triangles, but if we orient our cords diagonally, then the treads and risers triangulate the truss. So cantilevered folded bent plate. So this is interesting. Obviously, or maybe not obviously, but this plate is far too shallow to cantilever out of the wall like this, and yet it does. What we've done by interconnecting them and making this continuous ribbon, we get fixity at the end. So it can't rotate at the end. So instead of doing this, the stair is forced to do this. It bends in an S shape because the interconnecting plate prevents it from rotating at the end. That simple move doubles the stiffness of the stair right up. Well, no, dramatically, probably increases by 4 or 8-fold. Dramatically increases it by forcing it to bend into an S shape as opposed to simply a simple cantilever. This is Pengelly Ironworks at Antimex. So this is a steel stair supporting structural glass treads and landings. Oh, here we are. This is the cantilever tread again. So let's look at some takeaway tips. Basic loading for stairs. Stair generally, I'm sure that I'm going to contradict something Shannon said, but truth lies in between somewhere. Basic loading criteria for stairs. The stair is part of an exit path in a public building, which means it needs to be designed for 4.8 kPa in a public building if it's part of an exit path. So very high loading. In a non-public building, the stair is designed for the occupancy that it serves. So in a house it'd be 1.9 kPa, 4.8 in a public building. Serviceability is almost always the governing criteria for a stair, whether it be straight sag or vibration. Vibration is very, very often the key. Shannon talked about it. The 1 kilonewton, 1 millimeter is a really sound rule of thumb that is indicative of vibration performance. So keeping ourselves under 1 millimeter for 1 kilonewton for a stair with a low inherent frequency is probably not enough. Like that, we're not necessarily going to get there, but it's highly indicative. And for a stair with a high frequency, it's fine. Connections and sequencing are important. So we have to be mindful of when the stair gets built, because that'll drive some of the decisions on how it gets built. Working in based on the normal workflow, and precedent is helpful, but it can be misleading. It can be misleading because sometimes the load path is not what it appears to be. It could also be misleading because codes are evolving and they're becoming more stringent in a kind of a socially positive way, notwithstanding some of the pushback. It's socially positive. We're building buildings to be more accessible to people with various impairments, but that is limiting the way we can design. So
I feel like I want to add, because I sounded like I when I said that Dieter was critical of the new code elements, he's not critical of the ones that help impairments. That
Right.
isn't the thing that he's against at all with the code changes. I realized in retrospect that's what it made it sound like.
it's the whole baby head thing. To heck with the
Those
babies.
babies, they can look after themselves. No, it was more the ones where those situations are unlikely to occur or will not occur.
Yeah.
And they're still mandated for ones where, in situations where it's not reasonable. I found the missing dryer ball. Our kids must have found it.
Oh, nice.
Were you all done? Or
Yep, that's it.
All right. So next week, we will look at a lot of these same images simply because the guards and handrails go hand in hand with the stairs. But you can see just talking about the stairs was pretty much an entire lecture. Next week, I think we do, because guards and handrails, so much of the information is already covered and we've already looked at a lot of the images, and Dave can't help himself but talk about the guards in conjunction with the stairs because they are tied together.
Yeah.
I think next week we also do canopies.
Like separating the crust from the filling in a pie. I mean, it's a pie.
Exactly. Okay, so some of you may wander in and see me tomorrow morning sitting in the classroom. If I find that no one comes, which is fine, you don't have to come. I'm gonna work, and if you don't have a question, don't come just because you think you need to have to. We can maybe start to set up sign-ups the day before, so I know that it's even worth going in or not. It might not be worth me going in, and it might be worth me going in. It might not be worth me going in for the time that I need to get in there as well. So I can start to work that out as we go. All right, I'll be down there tomorrow or Thursday. I'll be down there Thursday, and we'll record another lecture next week.